let's move on to a slightly different scenario. We've talked about fatigue loading, but we talked about, so far, we talked about stress, which is here, is 0 plus sigma amplitude sine omega t. Okay, intentionally wrote the 0 there. It's just showing you that there is no mean stress, and it's just reverse loading, which means it goes from plus sigma A to minus sigma A. So this section is slightly different. We are looking at sigma as sigma m plus sigma A sine omega t. So sigma m is well, it could take any value, right? It is 0 or greater than 0. This is just showing you what that really means. This is the mean stress here. This is the amplitude. Okay, so this is related to the number of cycles approximately, right? And this is our stress, which we were looking at for SF and so on. Now we've added a third variable, sigma m. And now suddenly our life is going to get more complicated, as you'll see. It's, for example, when you try to understand a material, when there are just two parameters to be varied, sigma A and cycles, what you do is keep the stress constant and then keep increasing the cycles n till it fails. And remember, that gave us 1 point on that SN curve. And then we do it for a different sigma and so on. Now, if we add another parameter to the mix, sigma m, sigma A, we have to keep sigma m and sigma A constant, load the specimen with cycles till it fails. That will be 1 point. And then you keep repeating that for multiple times. So in order to understand failure, what we do is, 1, we'll choose sigma, we'll choose sigma A, apply sigma equals sigma m plus sigma A sine omega t for increasing n till failure. Okay, and then we'll just repeat for a range of sigma m and sigma A. Okay, so that's very easy for me to write it, but it's in principle a very costly and time-consuming process, right? Because you're trying to machine a specimen, keep sigma m, sigma A constant, load it to failure. Once it fails, you discard it, take the next specimen, you choose the sigma m, sigma A, increases the number of cycles, it fails, and so on. So this is like very expensive, and you probably don't want to do it yourself because it's going to take a lot of time. So if you have these plots, we can maybe do something with those plots for a particular material. So what I'm going to show you now is, I wrote it down already here. So what you see here is some data points, the squares and the triangles and so on. And these are plots made for sigma A versus n, but they are for a given sigma m. So when you keep sigma m, so let's say you choose a sigma m and a sigma A, and then this to get, so if I get this point, this is for a particular sigma m, sigma A till failure. So a specimen is dumped, new specimen is taken at this sigma m, sigma A, you do it. So now we have just shown a few plot points there, but to get that kind of curve, you need to probably fail a lot more points, have a lot more samples, right? Anyway, so what it basically says that everything lines up pretty beautifully. This stress here is our stress level sigma m equals 0. This is a special case which we talked about in the previous section. And then if you keep increasing sigma m, remember what's happening when you increase sigma m. As sigma m increases, your total stress is increasing by that value. So clearly, if your stress increases, then what you'll see is for a given, let's see, for a given sigma a, let's just draw a line. This is for a fixed sigma a. You'll see that this point has a lower life. This is the life for this sigma than this point, this curve. In other words, as sigma m increases along this curve, you will see that the life decreases, so because the total stress is increasing. And that's why they will be, as shown, they won't be, this line appears below that line because the stress here is much higher than the stress above it and so on. Okay, so it's clearly more, you have higher stress when you look at sigma m not equal to 0. So there's another, so this is a plot of sigma a versus n for a given sigma m. This plot has been redrawn in slightly different way. Here there's a plot of sigma a versus sigma m for a given n. This is the same plot as before, but with changed axis. And so you will not see, we had an SN curve. Remember, S was the stress, N was the cycles to failure. We will not see those kinds of plots in this particular section where sigma m is also varying. People typically like to have a plot of sigma a versus sigma m as a function of the cycles, as you saw this year. Okay, so these are, again, these are all empirical plots. Okay, the only thing I want to mention here, which is not here, is that we are also interested in infinite life. So this is showing you for low cycle fatigue, high cycle fatigue. But what happens if you keep increasing the number of cycles? You'll see that there is this line asymptotes to a line like this. This is the curve for n equals infinity. Okay, which is also known as the infinite life line. It starts same point here, but it is a straight line. It's a straight line. So it's a straight line connecting SE to SUT. SE is on the y-axis and SUT is on the x-axis. Okay, this line is kind of well known as the Goodman line. So it's a life at which you're guaranteed that the material will not fail. And it basically tells you the stresses, right? It tells you what sigma m and sigma a, you would have no failure. So as long as you are in this region, you will have infinite life. Right? So your stresses and your sigma a and sigma m should be in this region. Then you're guaranteed that it's not going to fail. And this is for a particular material. I think this was C. We are out of time. But next time I'll just go ahead, and this is like important because our designs are going to be based on this in another. So I'll see you on Wednesday, sorry, Friday. Okay. And then you can then draw contours of similar n. So starting at 1000, you go all the way to 10 raised to 6. So increasing n. And you can see as the cycles increase, the stress to failure, any of those points of stress to failure is going to decrease. So if you consider this point has a stress sigma A and sigma M higher than this point, because clearly as the number of cycles increases, you can only take so much stress. So the region, the yellow region, well, before that, if you join the line connecting SE, the endurance limit, we've computed that, SUT, which is the ultimate strength, then that line is called the infinite life line. That is, if you're on that line or below that, your specimen is never going to fail, no matter how many cycles you take it to. So the region, yellow region, is the infinite life region. Okay, with that, let's move on to modeling this equation. So this is just the same line. I've not drawn here. We don't have these curves. We only have that infinite life line here, which I said it's called the Goodman life. Infinite life. Okay, so if you want to model this equation of this curve, we notice that sigma SE is the intersection on the y-axis, SUT is on the x-axis. The equation for line passing through those 2 points is simply, so if you recollect, if you have a line in x, and B are the coordinates of intersection. Actually, they like to put A on the x, B on the y, then the equation is x divided by A plus y divided by B equals 1. So that's the equation of a line passing, which intersects x at A and B. So you can use similar logic here. Sigma M is the x-axis, SUT is the intersection, plus sigma A is the y-axis, the intersection is SE equals 1. So this is the equation infinite life for Goodman line. Okay, so when we want to design something, we want to always keep in mind the factor of safety. So the simplest way of introducing a factor of safety is that you, instead of being on this line, let's attempt to be on a line parallel to this line. So scale it down, the stress, by the factor of safety. So that way we have this margin. This is the design line. And that gives us a margin. So based on NF. So what we do is, in order to get that, we simply substitute. Let's see. So design. So what we do is simply substitute. We just have the definition for NF, which is now the fatigue failure of safety. So NF is the maximum stress, which is going to be sigma. So we just going to scale the stresses. So if SA is the maximum stress at failure, sigma A is the is the stress, which is the design stress. So we always want to be, sigma A should be less than SA by a factor of NF. And then same can be done for the other axis. So we have SM divided by sigma M. SM is SAR max stresses. Sigma A and sigma M are the actual stresses. These are the stresses where the material will fail. And so all we have to do now is to take that sigma A and sigma M from this equation. Let's call this 1, let's call this 2. Just substitute 2 in 1, and then we get an equation for NF, which is the design factor for fatigue loads. Okay, so let's do that. So now that line Goodman line with axis sigma M, and sigma A would be so since the stress at which it fails is we modeled it as SA and SM, that would be sigma A divided by SA divided by SE plus SM divided by SUT equals 1. But SA is other equation there. So that's from the previous page. Here. So SA is sigma A times NF, and SM is sigma M times NF. So we'll just substitute in. So we have NF sigma A divided by SC, NF sigma M whereby SUT is 1. And so if you solve for NF, you get an equation which looks like this. Sigma A divided by SC plus sigma M divided by SUT. Okay, again, note this might not be very clear, but any points on this curve are basically SASM. This is SASM, the ones which I put over here. And then when we're designing here, what we're doing is if we're getting out a line like this, and this point is sigma A, sigma M. So we have this safety margin, which will prevent the material from failing because we are not exactly on that Goodman line. So this is the this line. Let's call that. This might be easier. So let's call that line 1. And this is line 2. And this is basically line 1. And then this is line 2, which has the NF in it. So far we've only seen a factor of safety for static loading, which was SY or SUT sometimes divided by the stress. this one models the fluctuating loads. It takes into account SUT, which is a constant part, and it takes care of the fluctuating part, which is SE or sigma A. Okay, so that's one thing. Now, what I have shown here is, however, you see that the stress sigma M is positive. Okay, there's no meaning in having a negative sigma A. After all, what we are talking here about is something like this, right? Sigma, this is sigma M, and this amplitude is sigma A. So there's no real meaning behind sigma, negative sigma. Positive sigma, negative sigma don't really have any meaning because that's just the amplitude. We only interested in the sign of sigma A, not the amplitude. But we are also interested in curves which are like this. So this is minus sigma M. So this is the tension, and then this is the compression region. So you can extend this plot on the other side. And so what people have done is, instead of doing the experiments only in the first half, the first quadrant, you do the experiment in the second quadrant, and you get that right here. So this is a broader set of experiments done in the tension region and the compression region. Tension, compression. Okay, so this is the Goodman line. Different color. Okay, but this is the other line for, this is the continuation of the Goodman line in the negative region. I think it's called the same. It's just the Goodman line. It's just that it is in the compressive region. So what you notice is that it's like this, the slope, but it's constant in the negative region, which means that when you are compressed, it's only the alternating part. You notice here sigma A, which matters. Sigma M doesn't have any role. It's independent of sigma M. So in compression, it's only the fluctuating part which matters. It's not how much constant load you have. This plot, by the way, is normalized again, SUT, just so that you can plot all material on this. Since it's normalized, you can, this is representative of all the materials which were used in this test. Now, there are some points which don't fit. So these are outliers. So it's not perfect. This is, we just guess that this is a good approximation, but there are some materials which fail. And here you can see there are some materials which also fail. Same for this. Okay, and that's why you want to have the design factor, which will ensure that your design may be something like this. Let's say something like this. That way, you're never really in this region where there is this outlier, then you always say. But when you have the design, you'll see that your material will become bigger, larger, have more mass, and that's would waste material and so on. So you want to push that limit as much as possible so that you are up closer to that line, because that will make the design light. At the same time, avoid these spots so that you are not really letting your material fail. So I've written down the equation for the right side, the Goodman line. You can write an equation to the left side. It's pretty simple. It's just, so in the compressive region, we have simply sigma A divided by SE. You can see this is 1. That's just that. That's the simple model for compressive region. So that would be, if you can see this, A and B. So that's for A, B. And we wrote down earlier the equation for the right side line. So the tension region. So I just put that here just for completeness. that would be sigma A divided by SC plus sigma M divided by SM, sorry, SUT equals 1. That would be line BC. Okay, and then if you want to introduce a factor of safety, from this equation, you just have to put sigma A is n times sigma A, which we did done previously. Just NF equals SC divided by sigma A. So that just gives you this gray line, which is below the actual stress. This is the design equation. Okay, so that's just the fatigue loading. It tells you how to design the material based on fatigue loading. You have to compute SE, you need to compute SE. And of course, if you're in compressive region, you use this equation. If you are in the tensile region, you need to use the other equation, which I wrote, but there's a similar expression for NF, right? Right? Right, this one. Just put that there for completeness. Copy. Let me just refer that by equation number. I think we already have equation 1 and 2. That would be here, 3, 2. Okay, so the next thing is yeah, so this is, well, let me get to this line, which is another line. Now, we've only talked about using the endurance of fatigue. We check for fatigue and design based on fatigue, but we also have to take into account the fact that something can withstand static loads. That is, if it cannot it cannot bear static loads, there's no point in designing something for infinitely many cycles. So this is sort of going back to this time when we were in chapter 2 doing uniaxial loading. So we also design for static loading. And so these two will give us a way of thinking about design. So we also consider static loading. So the recollection is chapter 2. If you remember, we had a specimen like this. And then it was loaded. Okay, and then you remember there was a curve, something like this. So this is, we also need to consider that when we design, not just fatigue. So that equation, if you remember, was, so this was ultimate strength, but there was this point which was the yield strength, Sy. And so we said that it will fail in uniaxial tension or compression if sigma is Sy, yield strength. Okay, so in this case, we are loading this with sigma equals sigma A, or sigma M plus sigma A sine omega t. So when we're saying sigma A, it's really the magnitude. So the magnitude of sigma A is going to be sigma M plus, so it's going to be sigma A, so sigma M with the absolute sign plus sigma A, because sigma A, we said there's no meaning in saying a negative value because it's just the amplitude, but sigma M can have a positive or negative sign depending on the tension of the compression region. So we can put this equation here to get sigma A plus absolute value of sigma M is Sy Okay, now what is this equation? This equation is, this gives us actually two equations. This is two equations. One of the equations is sigma A plus sigma M equals Sy. And the one is sigma A minus sigma M is Sy. So when we try to plot these two equations on a plot of sigma A, I always have sigma M on the x-axis, sigma A on the y-axis. So again, if you remember, the way to think about these equations is if you divide them by sigma Sy, then you have sigma A divided by Sy plus sigma M divided by Sy equals 1. And the same for the other one, sigma A divided by Sy minus sigma M divided by Sy equals 1. And then I've told you that if you have an equation of that form where something plus something equals 1, then the intercepts on the x and y axis is Sy and Sy in this case. So all I need to do is Sy, and then just join it. So the slope of 1. And so this will be in the tension region. So sigma M is positive. Call this 4. Call this 5. So this is going to be equation number 4. Because sigma M is positive. And then we'll have a similar equation for the negative side. Sy, so this will be equation 5. Okay, so this is just telling us what will happen in this situation where you have a uniaxial test and the material will fail the moment you increase P to a level where it is, the sum is equal to Sy. These lines are known as the Langer lines. So we have Goodman line and the Langer lines. Okay, and then if you want to consider the design lines, so what design does is it'll try to keep your stress below this. So this will be your design line. So you have a margin to failure. So this design line is just obtained by taking the ratios, replacing sigma A with n times sigma A. So that gives me NF equals Sy. We'll use that for design, but if you want to analyze to failure, then you use this first equation. Okay, so we've talked about Goodman line for infinite life. We've talked about this line, which is the uniaxial tension line. This is also known as the first yield line. That means that if you have a stress big enough, then the material will break even before you apply the first cycle. So the first cycle failure, so before n equals 1, it will fail before you can even apply the cyclic load. So we are now going to combine what we have here, the Langer lines and the Goodman line, into a single plot because they are the same axis, sigma A, sigma M. And that plot looks like this. So this is a combination of the two. It looks it looks very crowded, but let me simplify this. Okay, so first of all, what we have here is, this is the Goodman line. Okay, you can recognize that it is constant on the negative sigma M axis. It is sloping on the positive sigma M axis. The points of intersection are SC and SUT. Okay, and SUT, remember, is always greater than SY because if you remember the curve for failure, SY is here and SUT is somewhere up. Okay, so SUT is greater than SY. The other line here is the Langer line, this one. You can see the intercepts are sy and negative sy on the x-axis. So you'll always see that this curve looks like the way it is drawn, which is the Langer line would have a bigger slope than the Goodman line. Okay, now we come to the regions, which I think is the most interesting. This is a very powerful figure because it tells you graphically what's going to happen. Okay, so if you are it's already shaded. So if you are in this region, the blue region, then it's saying that you're going to have infinite life. That is, no matter how much cycles this material is subject to, it's never going to fail. Okay, that comes at a cost. It basically means that your stresses cannot be very high, right? The stresses start at 0 and they keep increasing. So you're limited to all the stresses up to this limit. Anything above that, which is between the Langer line and the Goodman line, the region in gray, is called the finite cycle region. That means failure will occur from one cycle to infinite cycles. Not exactly infinity, but less than infinity. So countable. Yes. And then beyond that, which region is in white, we just shade that. So all this region, which is outside this gray or the blue, is called the first cycle failure. Okay, it's saying that it will fail here before even the first cycle apply. When I say cycle, it means cyclic loading. So that is the first cycle failure. So let me summarize this. Yellow, first cycle failure, n is less than 1. Gray is finite life. The cycles are between 1 and infinity. And then the blue is the infinite life.
So, Professor, I have a question. What infinite, like what number we will be like looking at? Like if it's greater than that, we will assume that's infinite.
Infinite is infinite, never fail.
But like it's saying n equals to infinite. So what exactly number we will be looking like 500?
Yes. Right. So it doesn't tell you, this plot doesn't tell you if it's 10,000 or 70,000 or 60,000. That comes from the other equation which we talked about. So how do you compute? How to compute n? So the way you'll do it is, I think the formula is SF equals a n raised to b, where a and b are constants which are dependent on functions of S, U, T, SE, and I think there's a small f. And then NF is, SF is going to be the stress. And then you can then compute n. That's how you'll do, that's how you'll compute n. This is something we've done in the past, but we'll come to a problem where we'll put all this together. So just bear with me. Okay, but that's how you do it. Now, there's something interesting going on here, which should be mentioned, which is it's right in this region. Okay? So you can see that if you want to do infinite life, then you're going along the Goodman line, but then there's this region where it's the Langer line which tells you infinite life. This is and so this Goodman line. So it's saying that it's going to fail here in fatigue loading, but once you reach at this point, it's going to start fail. It's going to fail due to uniaxial loads. It's not going to fail due to fatigue. It's the dominant mode of failure is not fatigue. So when you have a high stress, sigma is large, but not it's so big, but large, and sigma a is small. Right? Sigma a is this axis, so it's small, but sigma m is large. this is where you get this thing where you have the dominant mode is not fatigue, but it is due to due to static loading. So you need to be careful when you have large sigma and small sigma A. Okay, so what we're going to do with this is we can actually do some predictions based on this or design calculations. So imagine that you're designing a machine element and you are trying to figure out for the stress spikes, the stresses which are applied to that specimen. It could be fatigue or it could be static loads. You're trying to ask yourself, is it going to fail because of, before I even do the first cycle, the yellow region, will it fail in finite number of cycles, the gray region, or will it fail or it will never fail, which will be in the blue region? So that's a question you always have. So if you figure out that your specifications say it needs to last for infinite cycles, but then you figure out that it is actually landing in the gray region, then you need to do something about design. Maybe redesign the machine element such that you will actually end up in the blue region. So it's kind of important to keep that in mind. So what we'll do is I will show you how to figure out, okay, let's say that I've given you a machine element, I've given you the stresses, I'm asking you, can you figure out which region the material is going to lie in? Is it going to fail in finite cycles, or it's not going to fail, or it's going to fail in finite cycles, or it's just going to fail in the first cycle? So what you can do is you can actually use this plot to do it. This is the same plot, just cleaner version.